Hi, so this is a quick video for students who missed the Lewis diagrams notes. This is just a very, very quick video to help you either learn or remember how to write a Lewis structure. So the first thing to remember is that Lewis dot diagrams are basically just showing valence electrons. It's a way to simplify our model so we don't have to draw all the rings in every atom or ion. You should also know the octet rule and why it's for bonding. You should have a periodic table out for this. And you should know how to use a periodic table to find valence electrons for an atom. Okay, so first, the very basics. When I'm showing atoms to show charges for ions, atoms are going to have the number of valence electrons that the periodic table shows it has. So nitrogen, you should see, it has 5 valence electrons. So I'm going to draw 1, 2, 3, 4, 5. Technically, I can draw those dots anywhere I want, but it will help you a lot to, when you draw your dots, when you draw your valence electrons, to put one on each side and then start pairing them up. You basically only want to pair them if you absolutely have to, because what's going to happen is the dots that are not paired are going to be where you're going to start to see your bonds on your covalent bonds. But that's an atom. So remembering that nonmetals always gain electrons when they become stable. So nonmetals take electrons or gain electrons when they become stable. We're going to see that nitrogen is going to get to 8. Remember, the octet rule says that most atoms are going to get to 8. So it's going to gain 3. 1, 2, 3, 4, 5, 6, 7, 8. Since it has 8, it's going to have a charge. So I'm going to put some square brackets around it, and I'm going to write the charge. So it's a gain 3 electrons, so it's going to have a minus 3 charge. Okay. So quickly use your periodic table, pause the video, and do sulfur and bromine. I'm going to go and do this really quick, but pause the video so you can do this on your own first. Okay. So again, remember that nonmetals gain electrons. Metals are a little bit different. They're doing the same thing, but remember that they gain their octet by losing electrons. So metals lose electrons to become stable. Okay. So if you look at calcium, calcium has 2 valence electrons. I'm going to go and draw them both together just to make it more obvious that there's 2. Rather than separating them in this case. So calcium, it could gain 6, but it's better to lose 2. When it's done, it will have 8 valence electrons, but if I draw that, it makes it look like it gained 6, not lost 2. So when I draw my calcium ion, I'm literally going to draw nothing. I'm not going to draw any valence electrons because the valence shell disappeared, and it now has a new valence shell, which we are not going to draw. Otherwise, it's going to look like we gained electrons when we're actually losing them. So since it lost 2 electrons, it's going to have a plus 2 charge, and that's calcium. Metals are pretty simple. Okay. All right, so pause the video, do potassium and aluminum. When you're done, just look back, and I'm going to finish this right now. All right, good. So now, hopefully you guys can see, we can show the octet rule, how atoms become ions to become stable by having a full valence shell, by having 8. Okay. In the case of hydrogen or helium, it's going to want 2. Okay. So on the next page, we're going to take, excuse me, we're going to take, and we're going to draw formulas for these structures. This is where really Lewis structures become super powerful. Okay. So the very first thing we need to do is we need to make sure that we recognize from the formula whether the substance is a salt or whether it's a molecule. So remember that salts are ionic. That is a metal because it's going to lose electrons, become positive, together with a nonmetal. Molecules are going to be our covalent. This is going to be where they're going to share valence electrons. Okay? So we have to decide which one is it going to do before I even start drawing my structures. Okay? So sodium chloride, sodium's a metal, chlorine's a nonmetal, so that makes that a salt. Okay? Right now, go ahead and figure out what each type of compound is, pause the video, and then come back and check your work. So the first two are salts, the rest are molecules. And the main reason for this in this document is we really don't use Lewis structures for salts because salts are so simple. They do the same thing every time, and the structures are always positive, negative, positive, negative, positive, negative. But I find it useful to show with a Lewis structure how this works. So when I do sodium chloride, I'm going to have one sodium. Sodium comes with one valence electron. One chlorine. Chlorine comes with 7 valence electrons. So you can kind of see almost immediately how chlorine is missing an electron here. It wants to gain an electron. So this electron is going to move over, which is going to give each thing a charge, and the charge is going to be what makes them stick. So we're going to take that electron, we're going to move it over. We're going to write our brackets because now it has a charge. Sodium has a +1 charge because it gained an electron. Chlorine has a -1 charge because it lost an electron. So what holds this together is the charges, the positive and negative. The transfer electron gives them a charge, but they stay together because they have a charge. And that's an ionic bond. Notice I'm not drawing any other lines between them. The charges are showing me that they're sticking to each other. Nothing else. Okay. For potassium oxide, my next salt, it's the same thing, but notice in my formula I have 2 Ks and 1 O. I'm going to go back and forth between positive, negative, positive, negative. Since K is written first, I'm going to go write my K first. Potassium has 1 valence electron, so I know that when I'm done, it's going to turn to K plus. Oxygen has 6 valence electrons, so I know when I'm done, it's going to turn into oxygen with a 2- charge. I'm going to kind of do that all in my head because the metals are empty, and the oxygen obviously shows, although poorly there, that it has 8 valence electrons. Okay? All right. Then we're going to get into molecules. Molecules are really where the power of Lewis structures come in. We're going to draw molecules a little bit differently. So with fluorine, I'm actually going to draw my valence electrons and kind of move them around as I need to. So fluorine has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. When I look at fluorine, you can immediately see, hopefully, that it's missing an electron right there. It's missing a buddy. All of my electrons have buddies except for that one. Fluorine needs to take an extra electron. But what I have available is nothing other than another fluorine atom. So I'm going to go ahead and draw another fluorine atom. Here, I'm going to give it 7 valence electrons, but I'm going to put its lone buddy right there. 1, 2, 3, 4, 5, 6, 7. And now, when I look at each fluorine, this blue fluorine, when I look at the electrons, if it shares one, if it takes one from the other red fluorine, it has 8. If I look at the red, same thing, it also has 8 because those 2 in the middle are being shared. So to really emphasize that those are being shared, we're going to take and we're going to draw a line between them, one straight long line. And that line is going to represent our 2 shared electrons, otherwise known as a covalent bond. So molecules are always going to have covalent bonds. I want to make sure that when I draw my structure, I have the correct number of valence electrons. I'm not adding or taking them away. And I'm showing that sharing clearly. Okay? So let's try the next one. We're going to work on the next one together. When I have more than 2 atoms, the first atom is almost always the atom that's in the middle. So I'm going to draw oxygen in the middle. Oxygen has 6 valence electrons. 1, 2, 3, 4, 5. I have to pair up one more. Let's go and pair up the bottom one. Okay, so now it has 6 valence electrons. So hopefully you can see that it has 2 locations, 1, 2, where electrons are needed. We want to have that single electron be paired later on because it's going to help me see where my bonds go. Well, I have 2 fluorine atoms, so I can take my fluorine atom. I can draw one on this side. I'm going to make my fluorine blue. 1, 2, 3, 4, 5, 6, 7. I can look at my fluorine right now. It looks like it has 8 when I do that after sharing. So I can go ahead and make a bond. Okay. I'm going to do exactly the same thing to the other side. So I'm going to draw my fluorine. 1, 2, 3, 4, 5, 6, 7. That makes a covalent bond there. And that's my structure. Let me make this one a little bit darker so that you guys can see that it really is the same on both sides. And again, before I finish, I want to just double check to make sure that everything has 8 valence electrons. That oxygen has 8. Remember, each line counts for 2. Okay. So pause the video and then go ahead and try the next couple. I'm going to do the next couple really quick right here. But you should try them on your own first. So pause the video before you're watching the next part. Okay, so for nitrogen trihydride, notice that hydrogen only has 2 electrons. That's purposeful and that's perfect. Hydrogen is in period 1, and it has only 1 ring, and it is stable with 2 valence electrons. So this is actually what it wants. That is your structure for nitrogen trihydride. Carbon tetrafluoride is going to look like this when you are done. Hopefully that one was kind of easy for you. Okay. And then finally, we're going to do carbon dioxide. Carbon dioxide is going to do something a little bit new. So hopefully when you got to this one, you probably got a little bit stuck. If you got to this without help, you are amazing. All right, so carbon. Carbon goes in the middle. 4 valence electrons. I have 2 oxygens. So I'm going to pair this one up. 1, 2, 3, 4, 5, 6. Do the same thing on the other side. So often students at this point will say, okay, I'm done. I want to draw my lines. But if I look, oxygen's not happy. Oxygen only has 7 valence electrons. Carbon only has 6. I'm going to go ahead and draw my bonds. Okay. Just to make this next part easier. So when I look at this, oxygen still needs one more. Each oxygen still needs one more. This electron right there needs another one. Well, look, carbon. Carbon actually needs 2 more. It has 2 more that need buddies. So what we're going to do is we're going to take it and we're going to erase this one, and we're going to move it between the carbon and the oxygen. We're going to take one of carbons and we're going to move it between, and those are going to share again. This is creating what we call a double bond. Okay. I'm going to do that again over here. This carbon is going to move over. This dot electron is going to move over. They're going to create another bond. And so now, when I like my oxygens, I have 8 valence electrons. This one also has 8. And the carbon also has 8. Remember, each line counts for 2. And so this is my structure for carbon dioxide. I can do double, single, and triple bonds. For purposes of this class, you're generally not going to want to do triple bonds. I'm sorry, take it back. You will do some triple bonds, but you're not going to do rings. And most of the time, you'll just have single bonds. On an occasion, you'll have a double bond, and on a rare occasion, you will have a triple bond. But you are allowed to do them if needed. Good luck. I hope this works.